Alright, so we're going to learn how to derive the Feynman path integral. So to get started with it, let's imagine a quantum state called Qi, comma Ti, and it goes to some Qf, comma Tf. So with the Qi and Ti is basically a point Q at time t, and the same with the final state, point Qf at time t. That's the idea here, and so we're going to convert this from the Schrodinger picture to the Heisenberg picture. And that would require us to write this as a difference of time coupled with the Hamiltonian, the exponential operator. Basically, these states are time independent and the Hamiltonian is time dependent. The operators are time dependent. So what we want to do is imagine this line representing the time, right? T initial to T final. And what we want to do is create separations between these two discrete time steps. Um, I drew them unevenly, but still, imagine them to be discrete with um, a length of epsilon, and imagine there to be n such time steps between the initial and final state. That would mean that delta t, t initial minus t final, is nothing but n times epsilon. Or epsilon can be written as delta t divided by n. So we're going to use this and plug this into the uh, propagator that we have. And we have q final times e to the power minus I h delta epsilon times n ui. So we're going to write this as q final e2 minus I h. What we're going to do is multiplying by n is essentially like taking the exponent of n. So we're going to multiply this singular operator that is raised to the power of n times. We have e to the power minus I h epsilon times itself and such times. And we can, and of course, sandwich between the Qi state. So what we're going to do is take advantage of a very useful quantum mechanics property, and that's completion of states. So we're going to insert a Q position state between each of these operators. And we'll start from Qn minus 1 and go all the way down. The Qn minus 1 sandwich between Qi e to I minus I h epsilon, so on, all the way down to some Q1. Right? And sandwich that between Q1 and Q initial. And of course, if we are inserting completeness of states, we'll have to sum it over. In this case, it will be an integral. And the integral will multiply all the infinitesimal dqn minus 1 all the way to dq1. Now, we'll have to know what is the Hamiltonian of the system. So let's assume a free particle, so no potential, essentially. It will just be p squared by 2m. So the effect of that will be incorporated in. So we have integral dqn minus 1 all the way through dq1, and we multiply that with the before derived qf with the bonus I h epsilon, which will now be p squared by 2m epsilon times qm minus 1 and so on all the way to q minus 1 p squared by 2m q initial. There we go. So now, to solve this, what we're going to do is we'll generalize this integral, form a general sort of an integral. And we'll say it's in the integral over dqn, sandwich between states qn beta minus I epsilon p squared over 2m qn minus 1. This is the general sort of integral that we want to solve here, that is repeated throughout. the entire product of integrals. So now that we have a situation like this, and we have the p squared operator, naturally the thing we're going to attempt to do is insert a completeness again, but this time it will be a momentum space completion. So Qn e to the minus I epsilon p squared over 2n, but this time we insert p and replace that with Qn minus 1. And of course, since it will be completeness, we are integrating over dp. Now of course we know the action of p squared on its own eigenstate p. We leave us with just the p value instead of the operator at the top. So qn p qn minus 1, and we can drag the number out. It's minus I epsilon p squared over 2n. And this is just solved by the standard quantum mechanics result. It's going to be a position and momentum eigenstate inner product xp. It'll be e raised to the power of I q n dot p, and when it's and divided by root 2 pi, of course. And when it is reverse, it's going to be minus I p dotted with q n minus 1 and divided by root 2 pi. There will be an h squared, but we assume it to be 1. We have the regular minus I epsilon p squared by 2. Okay. So we have finally this result. And building it all into one singular exponential, we have e to the minus epsilon p squared over 2n plus taking p common, ip common, qn minus qn minus 1 whole. Now this is just a very standard Gaussian integral. Uh, it is usually of this form, so integral dx e to the minus ax squared plus bx. This gives us to be the result of pi over a under root times e to the power b no, minus b squared over 4ac. And in this situation it will be under root 2 pi m over pi epsilon times, and we already have the integral dqn over 2 pi, so e to the minus e to the I squared qn minus 1 whole square divided by 4 times AC, so 4I epsilon into 2m. So this will just solve out to m over 2 pi I epsilon and into e raised to the power of minus 2 to cancel out with the 4 there, so m times qn minus qn minus 1 whole square divided by I epsilon times 2, of course. Yeah. So now we have kind of a general result for the integral. So we can kind of write this back and say dqn times under root m. So we're plugging it back into the product. So we'll say dqn multiplied all the way to dq1. And since it will be m over 2 pi I epsilon, and since we're going from n all the way to 1, we'll say it's n minus 1 by 2 times e to the power minus, okay, we'll take I to the top and we'll say I m by 2 epsilon times summation of, we can say qn minus 1 whole square plus qn minus 1 plus qn minus 2 whole square, and so on all the way to, we'll say q2 minus q1 whole square. So this is the form that we have boiled it to. We can say integral pi dq n. Let's say it's n, small n. So n goes from 1 all the way to capital N. And we have m by 2 pi epsilon raised to the power n minus 1 by 2 outside times e to the I m by 2 epsilon. Let's write this as a summation. So we have qn minus 1 times qn minus 1 whole square. And the qn minus qn minus 1 whole square, and then goes from 1 to n, of course. So this equals pi n equal to 1 to capital N dqn. Let's say m by 2 pi epsilon is some b, and we say e to the I m by 2 epsilon. We'll multiply epsilon up in the numerator and the denominator, and we'll see why in just a moment. So qn minus q minus 1 whole square summation in there. Now what we're going to do is take this epsilon whole square and insert it into the expression, so that we have qn minus q minus 1 whole square divided by epsilon square. And of course, this whole thing can be written in a whole square, so that we get that neatly to the expression. So now what we're going to do is kind of take the constant with the multiplications of the dq's and call it a capital dq as e to the I m epsilon over 2 times summation, and this qn minus 1 whole square divided by qn minus 1 epsilon, all that in the whole square. So this kind of a general expression we got now. We're going to take a limit from limit epsilon tending to 0 and n tending to infinity, which is basically the equivalent of saying all these discrete time steps that we define. They all, instead of having a defined length, they're all going to be continuous like this. So we'll say this is equal to integral dq e raised to the power I m over 2. Now we know that this is a definition of an integral in terms of the limit sum. So this can be converted into an integral. The little epsilon out there can be written as dt, dt, and since delta t is epsilon times n, and it has dimensions of time, we can write this as dt. And the little qn minus q minus 1, it is basically the definition of a derivative as epsilon tends to go to 0. So we can say dq by dt whole square. So finally we can say dq e to the I m over 2 equal dt q dot square. And now this is starting to look a little familiar. It would have a potential there like that, and it would pretty much be identical to the Lagrangian. So I am by 2 integral dt Lagrangian. That is the Lagrangian. So I have integral dq e to the I m over 2 s of q. Alright, so the mass does go into the Lagrangian. Call this for that. So we'll go mq dot square over 2, and I will kind of be lingering outside there and lonely. So we'll go e to the I integral dt, which is just the action, which is the propagator that we defined initially. U final comma t final, U initial to t initial.